Thank you very much for coming. Good morning, everyone. This morning we're going to hear from Michele Mesiti about aspects of clustering algorithms, a journey between statistics and scikit-learn.
Thank you very much, Ed. So, so just to make things clear, this talk has been produced based on my limited experience, which is amount to some months here and there, trying to use clustering algorithms and to code my own stuff. So the intent is to show something that I hope will be interesting to an audience and not to teach anything to anyone. Just because I'm not an expert on most of the topics I'm going to talk about, but that's possibly the spirit of the tech chats. Okay. So basically my talk is divided in two parts. There is a part which is mostly about theory in a sense. What clustering means intuitively. I will talk about some methods which are in scikit-learn.cluster, which is possibly the most readily available library that contains this kind of algorithms. And there's a lot of algorithms there. But I will focus on only some of them, which are, I think, the most common. And then I will talk about the clustering problem from a point of view of Gaussian mixtures, which allow us to have a nicer statistical treatment of it. On the other hand, it's a bit restricting because we are going to assume that everything is Gaussian. After that, I will talk about the expectation maximization algorithm, which I had to implement myself just because I wanted to see how it worked, and also because I need to create a more complicated version of it for applications. So in the applications, I'm going to talk about the group-based trajectory clustering, and we'll also talk a bit about the context of it and the implementation. The group-based trajectory clustering is basically a kind. The way that I've understood it is a kind of Gaussian mixture model. Moving on. So about clustering, what does it mean to cluster data intuitively? Well, the idea is to group data based on some notion of proximity or similarity. Of course, the proximity idea needs a kind of metric. Okay, and in order to have a metric, we need to specify it. Most of the times, we are fine with the Euclidean metric, but there are a lot of cases where this is actually not true, and there will be some examples of this in a moment. And the other thing we want to do is to actually extract structure from the data in order to describe it synthetically. This will be clear in a moment when we see some example of this. This is a picture that comes from the scikit-learn website, which compares all the different clustering algorithms and their results on different kind of data. For example, we are going to talk about the k-means algorithm, okay, which is of which the mini-batch k-means is basically a very highly optimized version, and we're going to talk about the affinity propagation and spectral clustering. I would like to mention, to point out this, that, for example, here in the first example, we are talking about clusters which are not convex, okay? And a lot of clustering algorithms have problems with clusters which are not convex. So k-means has a problem with it. Affinity propagation as well. Also Gaussian mixtures, they assume that the clusters are blobs that resemble some kind of multidimensional Gaussian distribution. And instead, it's quite nice that spectral clustering gets that, and I will discuss a bit about that. And one thing I will not be talking extensively about, because I haven't used it and I haven't actually looked into this enough, are hierarchical clustering algorithms, of which agglomerative clustering is an example. And but I think it needs to be there. Yeah, I will possibly get back to this picture later on, just to compare the items. Unfortunately, I don't know if there's any way to. No. Yeah, there is actually another line in the slides, which has disappeared. Well, anyway, moving on. So, what about this library, scikit-learn.cluster in general? So, it contains a lot of algorithms which have a similar interface. The usual way of using it is, just to initialize a clustering algorithm object, where clustering algorithm could be k-means or spectral clustering or whatever. Okay, with the right setup. So, for some of the algorithms, you have to specify the number of clusters you want. This is also one thing to discuss. There are some clustering algorithms which need you to specify that number of clusters before, okay, and some who don't, and they instead rely on other parameters to decide what is the correct number of clusters. And another thing you may want to do is, instead of passing the features, the data that you want to cluster, you may pass directly an affinity matrix. Okay, we'll see later what it means. And then once so you specify this with this parameter usually which is affinity precomputed. Okay. Which means that I'm not going to pass the algorithm my raw data, but I'm going to pass an affinity matrix. Step 2 is to actually call the fit function on this object, on this clustering algorithm object, and passing x as an argument, and x can be either the data or the affinity matrix that has been precomputed. And eventually, you get after this, you get some results, which is usually an object that contains the labeling, and maybe children if you are talking about an agglomerative clustering, if you're using a hierarchical clustering algorithm. So, about k-means. K-means is the workhorse of clustering. That's possibly the simplest algorithm, and it's also the fastest one. Even when you don't want to use k-means, you may want to use it at the beginning just to initialize your clustering algorithm. That's quite intelligent things to do that I have learned only recently, and for this reason you will see what happens if you don't use this as let's say improperly preconditioned. So so you need to choose the number of clusters beforehand. By points here, I possibly meant the center of the clusters. Okay, and it's kind of a hard clustering in the sense that each point belongs to a single cluster, right? And the point here is that you want to minimize this inertia quantity, okay, which is basically the sum of all inertias of all the clusters, right? So mu j here is the center of the cluster, and xi is the coordinate of the point. Of course, this xi is we are taking only the points that belong to that cluster, to cluster j here. Okay, and this is just for a single cluster. Okay. Wait a moment. Okay. No. Okay. So yeah. Anyway, that's the inertial matrix we want to minimize that. It's really fast, and it can be optimized further by using a mini batch scheme, where basically we don't process the whole data set at the same time. We just select a random subset of it, and we run k-means on that. It works. It can work really well if the number of points we have is much larger than the number of clusters we want to have, because then, I mean, what we basically need is just a few representatives for each cluster, and then of course, well, if you use less data, the algorithm is going to be much quicker. And there are also implementation with the stochastic gradient descent, which means that I mean, we can optimize this with computing the gradient in a stochastic way with batches basically. And if we merge with these two approaches, we get a very highly scalable algorithm and very fast. There's this article for those who are curious. So how does k-mean work? So we have an algorithm which is usually referred to as a Lloyd's algorithm. Basically, you first choose a number of k cluster centers, and you assign each point to the closest one. Okay, and then you recompute the cluster centers as a center of the mass of their own cluster. Okay, and you repeat 2 and 3 until the centers no longer change. And this is going to happen in a finite amount of steps. And when you got there, you have a labeling, right? You have a possible labeling. The thing is that these kind of algorithms tend to get stuck in local minima quite often. So in order to mitigate this, you just do random restart. So you start many times, and you see when you get the minimum, the real minimum of this objective function, of this cost function. Okay. Choosing the center positions at the beginning can be done in clever ways. For example, you may do it totally random, or for example, you can try to make them so that they are actually far apart, so you don't just put all the centers in one place. And this is going to speed up convergence quite fast. It has been proven. There's a paper on this in the bibliography at the end. So this is more or less what you get. Basically, if the axes represent the centers, basically, well, all the different the figures which are with the portions of the figures which are called differently represent the clusters basically. This may not be what you want, but yeah, that's how k-means work. And you can think. I mean, you can see here, if you have any familiarity with computational geometry, some Voronoi diagram, and that's exactly what it is. So going on, so there's another algorithm which works in a totally different way, which is called affinity propagation, and it's quite interesting. So you start from a similarity matrix. The similarity matrix basically usually amounts to the negative, the opposite of the square of the distance between points. So you have 2 points. For each pair of points, you compute the distance, you take the square of it, and you negate it, and you get S, which is this similarity matrix. And this similarity matrix doesn't change, okay, during the algorithm. But during the algorithm, we have two matrices. One is called availability matrix, and one is the responsibility matrix. And there is basically an interplay between these two matrices, where basically, well, you update A from R and vice versa. And this procedure is, this procedure converges to identify some exemplars. So what I mean by this? So basically, these availability matrices represent the term IK in the availability matrix A represents basically the availability for the sample, the point K, to be an exemplar for point I. Okay, and instead for the responsibility matrix, the term Ki will be the responsibility that K has towards I for being an exemplar. Yeah, so basically the notion, the most important notion about affinity propagation is that you have these exemplars, okay, where basically each cluster is represented by a real point in the data set. Okay, there's an algorithm which was which basically this is based on, which is, I mean, that inspired this, which is called k-centers, okay, which is different from k-means because k-means uses computes the center of the clusters based on this. The center of the clusters are not actual points; they are just averages. They are the center of mass of the blobs. Instead, here in k-centers, we have that each center of the cluster is an actual point. Okay, and affinity propagation is actually a faster way to do this, and faster and better ways to do this. Yeah. So that's what happens with affinity propagation. So basically, you can see we have, in this case, 3 blobs and each of 3 clusters, and each of these has a representative which is in the center. It's interesting to notice that actually affinity propagation doesn't require us to specify the number of clusters beforehand. There are some parameters in actually the way we set up this the similarity matrix, okay? And yeah, because the diagonal part of the similarity matrix is undefined. It will be like 0 or yeah. But you can actually set it to a value that to values that you want, and you can specify so how likely each point is to become an exemplar eventually. So yeah, basically there is some freedom in setting up the similarity matrix that, you know, if you look at the algorithm, you see that, yeah, it can lead to different number of clusters. So another argument I want to talk about, just because it's quite interesting, because it allows us to treat quite efficiently the case where clusters are not convex, is spectral clustering. So it's graph-based clustering in the sense that a lot of the intuition that comes to understand it comes from graph theory. So we start from n times n affinity matrix. It's a bit different from the similarity matrix. The similarity matrix is basically just the logarithm of this. Yeah. So the affinity matrix is can be set to be this. This is just, you know, the exponential of the Euclidean distance between 2 points. So xi and xj are actually 2 vectors. Okay. And yeah, so what's done is then to compute a kind of Laplacian related matrix L. And basically, well, so the important bit here is this D. This is a diagonal matrix, which has on its diagonal the sum of each row of A. So basically, Dij with I different from J is 0, but Dii for a specific term on the diagonal is equal to the sum of all the values in a row of A. Okay, and yeah, so this algorithm proceeds in a way which is a bit strange and difficult to understand if you just look at this, which is find the largest eigenvectors. You can prove that the eigenvectors are going to be bounded from above to 1. Yeah, you get these eigenvectors, you stack them vertically and normalize the rows. Okay, and if you normalize the rows, you're going to have a bunch of vectors which are of length 1. Okay, so they lie on they will lie on SK, so on the sphere in key dimensions. Okay, and then they will magically cluster. They will be clustered in different points. Okay, around the sphere. And then you can run the k-means or algorithm there, and you will find out, you know, that, you know, what each of these row is, what cluster each row is connected to. It's easier to see that it works on block diagonal matrices. So, and in this case, of course, this matrix is never going to be block Yeah, block diagonal matrix. Yes. This case is not going to give you this expression is not going to give you a block diagonal matrix. But you can expect that, for example, when xi and xj are far apart enough, this aij is going to be small enough. Okay, and so if you think about A as a block diagonal matrix, you will find that I mean, it's easy to notice that basically for each of the blocks you have an eigenvector and an eigenvector which has an eigenvalue which is 1. Okay, so basically for each of those blocks, okay, which will represent the clusters eventually. Okay? If you have a matrix, an adjacency matrix which represents a graph, and this is the block diagonal, it means that you have for each block you have a different cluster. Yeah. And for each of these, you will have an eigenvalue which is an eigenvector which is related to an eigenvalue of which is equal to 1. And yeah, so basically this is the motivation behind this algorithm. It was it's evident that it works for block diagonal matrices. The fact that it works well even for matrices which are not block diagonal can be proven using a thing which I didn't know it exists, a theory which is called matrix perturbation theory. So you basically look at the eigenvectors and how these eigenvectors change and eigenvalues change when you do some small perturbation on the matrix. So basically, what you have this matrix, this is not block diagonal, but it's almost block diagonal. So if it's block diagonal, you know that they are going to have these clusters. It's not block exactly block diagonal. What's going to happen? Yeah. Yeah, and the result is actually quite interesting. So you can have clusters of very very strange size, and yeah, it's really great. If this is the problem that you're looking at. So if you want to cluster, to have clusters of this size, of these shapes, then yeah, spectral clustering works well. Of course, well, from a computational point of view, the problem is that you need to compute the eigenvalues and eigenvectors of the matrix, which is non-trivial, and so there are some performance considerations here. So the sparsity of the matrix helps. Yeah, I mean, if the matrix is sparse, then this algorithm tend to work well. I mean, the fact that if the matrix is sparse, then it's basically it represents a graph with which is not too connected, right? Which has low coordination point, which is more or less what you would expect. So yeah, I would say the spectral clustering is for those kind of problems where you have an affinity matrix which is sparse. Yeah, and then it works really good. So another thing I don't have time to talk about, and I didn't have time to actually read much about, but it's really important. So there are algorithms that allow us to do hierarchical clustering. So here we don't have to specify the number of clusters beforehand, because basically based on the scale, okay, or based on some kind of metric that we decided we can agglomerate clusters together. So first, the idea is that each point starts in its own cluster. There's a bottom-up approach and a top-bottom approach. In the bottom-up approach, you have that each point starts in its own cluster, and then each cluster start expanding, and then they are combined together. And if you want, you can cut this dendrogram at a certain level, and you get a predefined number of cluster. The number of cluster that is relative to this level. And it's quite, I think that when you have no idea about what the data looks like, this is possibly one of the first things you would like to do. Because you don't know the number. If you don't know how the data looks like, you may want to actually have just a brief overview. before deciding how many clusters you want to have. And this sounds promising to me. Unfortunately, I have no experience in using this and haven't looked into the theory too much. Moving on. So from now on, everything is going to be Gaussian. I'm going to talk about Gaussian mixtures and the expectation maximization algorithm. So let's correct this slide, and yeah, so this is going to be only Gaussian, which is, I mean, it's a big restriction, right? Because as we saw, for example, in these cases, well, these clusters are not Gaussian at all. Okay, so this is a I'm basically changing the problem. It's this clustering in a sense, but yeah. Actually, to be honest, to be precise, in scikit-learn, in scikit-learn, the Gaussian mixtures are not in the clustering library. They are in their own mixture library. Anyway. So, why would one like to use Gaussian mixtures and do basically fit a distribution on the data, fit a Gaussian distribution on the data? Well, the thing is that out of this approach, we can get we can do some model selection based on some kind of information criterion. Okay, so we can we'll see later what this means exactly. So I mean this is quite slow though, and it has troubles with non-convex clusters because everything needs to be Gaussian as well. So, yeah. So what I have, the reason why I got interested in this is that actually I wanted to basically learn about trying to reproduce some data, some results that come from group-based trajectory clustering, and it looked to me like a Gaussian mixture problem. Okay, and so I wanted to re-implement one of these algorithms to understand how it works, and then try to improve. To basically extend this to the group-based trajectory modeling, which we'll see later what I mean by that. Okay. So, what is the Gaussian mixture? Basically, what we have a likelihood L, okay, which is a product for all points, okay, all points in all the my data set. Of a sum of probability that each point belongs to a given cluster times the the likelihood that that point is assuming that the cluster is that the point belongs to that cluster, then what is the probability that this is a Gaussian probability distribution, right? So just to talk about what is what here. So AC is the inverse of the conventional matrix for the Gaussian cluster C. I mean, you can have, because these the clusters which are represented by Gaussian distributions can be of different shape, right? They don't have to be spherical symmetric. They can be elongated in one direction, whatever. Of course, it must be definitely positive. Okay, so the second sentence doesn't make any sense because it's just a copy of the previous one without, yeah. So the third one is that makes sense. So the delta PC, that xPC is the vector between the position of a point, between a point and the center of a cluster C. And W, PC, is the probability that the point P belongs to cluster C. Okay. Yeah, now, what we want to do with this is to basically maximize the likelihood. So this L is a likelihood. It can be seen as a probability in terms of the x's. Okay. So given my cluster, the position of the clusters, the covariance matrix of each cluster. Okay. If I get that as an input, okay, then L here represents the probability of seeing the data that I see, seeing x given AC and also WPC. Okay. But I want to interpret in the other way, in the opposite direction. So, basically, I want us to take the data as given as the input, okay, and then as at the fixed set of information. Okay. And then I want to compute this quantity as a function of the covariance matrix and the centers. Yeah, so the centers which are not shown here. Okay. And I want to basically maximize this as a function of maximize this as a function of A, the covariance matrix, and the position of the Gaussian, the centers of the clusters. So in order to do this, what is usually done, in principle, it's possible to do a constraint minimization. So I can say, okay, the sum of this WPC for each cluster, for each P needs to be 1. Yeah. So the probability that a given point belongs to any cluster, okay, is 1. So the sum over C, okay, just this bit, okay. The sum of WPC for C that goes to 1, 2, and C, but this bit needs to be 1. Of course, well, this part which makes everything non-trivial. Okay. So in principle, I could do a constraint minimization of this under the constraint that W needs to be, that the sum of WPC for C going to from 1 to NC needs to be 1. But it's quite difficult. So what is usually done, we are using an expectation maximization algorithm, which is basically made of 2 steps. So there's the initialization, okay, which can be done in more or less clever ways. The clever way of doing it is to use k-mean and compute an initial clustering, and etc. Or the other option, which is the one that we did before knowing this trick, was to actually randomize it completely. But well, this slows down conversions quite a lot anyway. And and then after initialization, we enter a loop where we compute the expected values of WPC for each point P. Okay, so the expected values mean that basically we integrate over all possible cases, and for each WPC, this is going to the sound of it is a bit more. This sentence sounds a bit more daunting than it actually is. It's just basically replacing WPC with a normalized version of this Gaussian. So basically, the probability of a point belonging to a cluster is going to be higher if the point is closer to the center, right? So we compute this WPC first, and then once we have this WPC, we can actually maximize L, tweaking this A, the covariance matrix, and the position of the centers. Okay. We repeat 2 and 3 until convergence. Here, convergence does not happen in a finite amount of steps. Okay, you need to decide at a certain point that you're fine with the solution you got. And as with the k-means, this is just a sophisticated version of k-means, basically. As k-means, these can be stuck in a local minimum. So in order to get to the global maximum, you need to you need to do random restarts. So I have a little demo about this, just to show how things work. And okay, let's make that climatic. So this is a quite simple example. It's not always. So this is some artificially produced data. There are actually 4 blobs for clusters, and basically I'm producing 4 clusters at the beginning, right? And I'm just mixing them and removing any label information. And then I'm running this expectation maximization algorithm on it so that we'll find the clusters doing. So basically I'm plotting the results of the clustering every 10 steps of this maximization of the algorithm. And you can see that actually, so each color corresponds to a label, basically. Here's funny. I mean, I don't know if you see that there was this kind of tension with a bit of time. So each point is assigned to a cluster. I mean, it can be assigned to more clusters, right? Because the probability is not always or either 0 or 1. It can be, it's a soft kind of cluster. So, for example, in this case, you can see that these points were actually not assigned to the blue cluster exactly, not to the green. They could, yeah. Anyway, I can stop this now and get back to the presentation. Yeah. So, so the thing that actually I wanted to do from the very beginning was to actually run this and basically fit this model on some data, which is the econometric data that I mentioned sometimes. And yeah, so basically, what is this about? So basically, I need to cluster multivariate time series. Okay, so time series which are not very long, like 35. They have 35 data points per latest. But they are multivariate, so they have actually more outcomes per. Yeah, I mean, let's say we have like in the case I'm interested in, we have 35 years. We have a data point per year. And this data point lives in a multidimensional space because we have different quantities that have been measured every year. Okay, and I basically would like to do a polynomial fit on these functions. Okay, and on this data. Okay, but the thing is that for each individual, for each entity, I have more polynomials. More functions that live in. Basically, I have a function per variable. Okay, and yeah, so it's a bit more complicated. So it's I mean, it's nothing particularly complicated from the point of view of. I mean, it's not something qualitatively different from Gaussian mixtures. Except for a couple of things which will be clear once I show the. So this L is actually the logarithm of the likelihood, okay, and yeah, I define it like this. So this L is actually a bit different from what it was before, okay. So basically, I'm summing on over all trajectories. Trajectories here represent points. What were points in the Gaussian mixture example before? Okay, and there's just a logarithm because I want to work with logarithms for reasons that will be clear later. Okay, and so this term with the logarithm of WCT is exactly the weighting, the weight that was before and was like the WPC instead. Okay, so this is the probability that a certain trajectory, a certain entity that evolves over time belongs to the cluster, to cluster C. Okay, and then there is this this term here, which can be which is expanded to this. Basically, so there's this term here, which is related to the spread. Okay. And so the spread here it needs to be noticed that the spread can depend on different things. So in this case, it depends on the outcome, so the variables. So for the different variables, I have a different. I can have a different spread. Okay, it can depend on I, which is basically the time. Okay, and Notice that here the time could also, all the data points may depend, the position of the measurements in time may depend also on the outcome. Different outcomes could have been measured at different times. Okay, it's not the case for what I care about now, but yeah, that's a possibility. And here, well, this is basically my distance definition. Okay, where I have this is the empirical data. Okay, this is the data which has been measured for a given outcome at a given time with this IO, and for a given trajectory, for a given entity. Okay, in my case, regions, they can be individuals or whatever. And this is instead the expected value, okay, given the polynomial. So this is actually not the whole picture. This is a bit simplified because, in principle, I mean, this is done using the Gaussian distribution. What needs to be done then is, I mean, it's a bit difficult because how do you cope with the missing data in this scheme? So you need to do some modifications. But yeah. Anyway, so I'm going to talk a bit about the implementation details of this. So I implemented this from scratch in Python. Okay, so there were some issues. For example, so should sigma depend on x, on the cluster, on the outcome? So I needed some flexibility. At a certain point, you may remember that I bothered you with this kind of, so what do you think should be the best way to code this? So do you like this kind of code? And it was because of this, because I needed some kind of flexibility in the way that I was storing these parameters. The problem is also that, so here, I need to point out this. So there's, in the expectation maximization algorithm, which is the one that I'm going to that I've used here, there is the expectation part and the maximization. So the maximization step here is it's more complicated than in the simple Gaussian version, right? And because it's because this is much more complicated. I have more. I mean, sigma is can be different. Also, you have these parameters which are the polynomial coefficients. You need to change them in order to, so maybe there are clever ways to do this, but the way I decided to implement the maximization step was just to take this function, okay, and use scipy optimize.minimize to try to minimize the thing, yeah, and yeah. So the convergence of this step, or just the single maximization step, is quite slow without providing the Jacobian. So what I had also to do was to derive this thing for all the parameters, along all the parameters, and then provide also a vector, not only just the value of this to the minimization algorithm, but also the Jacobian, so the gradient of it. So I had to implement all this. So yeah, the Jacobian is indeed quite complicated to compute, and it needs some unit testing. But the test is really easy to write because you just, if you want to just compare you need to compare the numerical derivative with the real derivative, and it's quite easy to do. You need to do it for each direction for each parameter separately. I was quite surprising that I mean once I wrote this I implemented in code this the derivative of this. There was only one mistake, and it's quite initialization with k-means is actually crucial to work for working with real data. If you don't, maybe you converge, but in a million years, there's this problem that that in principle this algorithm should converge, but it's slow. Second slide on this. So the choice of the minimization algorithm has also been quite important. I have used this BFGS, which I don't remember exactly. I think these are surnames of people, and it actually works very well. There's another thing that needs to be taken care of, which is taking into consideration that actually we are working with exponentials and logarithms of large numbers. Okay, and these things tend to overflow pretty often. Okay, and so when possible, you work with logarithms. And there are some issues, for example, here because you have to actually sum some exponentials. Okay, so you need to exponentiate and then sum, and well, you need to be careful because these things don't commute. So you need to. Then there is also the problem of missing data. Okay, and yeah. So in order to accommodate this, the missing data, you need to change the formulas using a sensor normal distribution. The sensor normal distribution is basically a distribution where if something some data is missing or is too far from the mean, okay, you just replace it with a data point which is at the edge of some interval that you decide. And that's what is done normally. And it's quite nice. I mean, this doesn't complicate the algorithm too much. You just need to be able to, just replace all your non-values with with the ones that with the one at the threshold. Yeah. So I hope we will have some time for a demo. Will I be able to? So so this is going to be a bit ugly. Sorry. Let's see. So okay. So this is basically what the kind of problem I'm working on. So this is some data which has been produced artificially. Okay. I have basically x goes from 0 to 35 for every outcome. We have 4 outcomes. The outcomes are the figures. Okay. The clusters are the colors. Okay. And so the idea is that now, if I remove the information about the clusters, so the colors, can my algorithm get back to where to this information? Yeah. Now, I just want to say, so this is this data that has been produced is quite actually stupid. Instead that using this approach here is not the best thing, because if you see all the sigma is equal everywhere, okay, and for this k-means would really work. If you actually run just k-means on this on this multivariate time series, you get exactly what you want. But nonetheless, so let's move on. To move on, I have to actually close all the windows, and yeah. So this is the first step, right? And it's struggling, trying to reconstruct the cluster out of this, and well, progress I still need to. You see here, for example, it went. It just in this case it failed. Okay. Or maybe it didn't, but you just need to backtrack at a certain point. Yeah. So this is still a second attempt. This is not really a second attempt. This is just a second step in the expectation maximization algorithm. We are close to the end. Still. Yeah, and we got it basically eventually. Yeah. So I can tell you that without actually having the Jacobian, it would be really hard, right? Or almost impossible. Yeah. So this concludes my presentation. Yeah, I hope that we have a bit of time for questions. Yeah, 7 minutes for questions. Yeah. Thank you.